Okay, last day we looked at vertical asymptotes. Today we're going to look at horizontal asymptotes. So this is section 5.2, and after this we'll go back to chapter 1 again. Okay, so we're going to get a horizontal asymptote when we graph this. Let's do that now. Let's graph it. And let's graph it by doing a table of values. So a good value to use to start probably is 0. So we'll put 0 in there. 0 squared is 0 plus 2 is 2. 0 squared is 0 plus 1 is 1. 2 over 1 is 2. Okay, let's try 1 next. And if you look, the two input values, the two x's, are both squared. So that can be useful to us because if they both have even exponents, that means whether it's positive or negative, you're going to get the same thing, right? So we can get two values at once here. So if we put 1 or negative 1 in here, but might as well put 1, it's a little bit easier. 1 squared is 1 plus 2 is 3. 1 squared is 1 plus 1 is 2, so we get 3 over 2, which is 1.5. Okay, just to speed it up again a little bit, we're going to do plus or minus 2, plus or minus 5, plus or minus 10, plus or minus 100, and plus or minus 1,000. And don't worry, I'm going to speed up here. So 2 squared is 4, plus 2 is 6. 2 squared is 4 plus 1 is 5, so we get 6 over 5, which is right around 1.2. Actually, it is 1.2. If we put 5 in here, it gets harder to do this in my head. You get 27 on top, you get 26 on the bottom. You end up getting a decimal 1.038462. I think that's more than we need. If you put 10 in here, you get 102 over 101, which works out to 1.009901. If you put 100 in here, you get 10,002 over 10,001, I think. You get 1.000100. And if you put 1,000 in here, I think you get 1,000,002 divided by 1,000,001. So you get 1.000001. Alright, so let's graph these. We have 0, 2. You have 1, 1.5, which is here. And you also have negative 1, 1.5, which is there. 2 and 1.2, and same with negative 2. 5 and just a little bit more than 1, and same with negative 5. 10 and even closer to 1, and negative 10. 100 and even closer to 1. 1,000 and even closer to 1. How close can we get to 1? As close as you want to get. Will you ever get to 1? No, you're never going to get there. So this is where we get this horizontal asymptote. The graph looks like this. It's very hard for me to draw, but it's going closer and closer and closer to 1, but never actually getting there. And the same over in this direction. It's not very good. And so what we also might want to draw here is the actual asymptote. I'll draw it right here. This is where y equals 1, and that is your horizontal asymptote. Why is it an asymptote? Because the function is getting closer and closer and closer to that particular line, but it's never going to reach it. So now that we've seen that, we can write a couple interesting limits here. One limit is the limit of this function, x squared plus 2 over x squared plus 1. Of course, I could have just written the limit of f of x here and saved some time, but I want to be very clear what I'm talking about. So the limit of x squared plus 2 divided by x squared plus 1 as x approaches infinity. So what does that mean? That means is we go further and further out to the right here, like out to infinity. So humongous numbers, giant numbers. What is this function getting really, 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 really close to as we go way, 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 way out there? Well, it's getting very, very close to 1. It's getting close to the asymptote. So the limit as x approaches infinity is 1. How about the limit of this same function as x approaches negative infinity? Whoops, negative infinity. Well, that means when we're going way off to the left, way, way, way off to the left. Where's this red function getting closer and closer and closer to as we go way off to the left? It's getting closer to a y value of 1. So again, we get equals 1. Now, these two don't have to be equal to each other, right? It's possible that just one of them equals 1 and one of them doesn't exist, or one of them equals something different. We'll show you a couple of examples of that just in a second here. So what these are called limits at infinity. Hopefully that makes sense because you're going out to infinity or to negative infinity and you're seeing what the limit is. And the way this is drawn, or the way this is written, just as I did above, it's written like the limit of some function as x approaches infinity is equal to L. In this case, L was 1, but it could certainly be something different than that. And the other one would be the limit of f of x as x approaches negative infinity equals some amount like L. The way we say this, the first one, the limit of f of x as x approaches infinity is L. And the second one, the limit of f of x as x approaches negative infinity is L. You could also say, instead of saying as it approaches infinity, you could say as it increases, well, I'm sorry, that says increases without bound. And for approaches negative infinity, you could say decreases without bound. But I tend to always say approaches infinity and approaches negative infinity. So decreases without bound is the other way you could say that. So if someone's talking about that, you know what they're talking about. What else did I want to say about that? The symbols infinity and negative infinity are not numbers. I tried to hammer that into your head last day, and I'll do it again today. They're not numbers. Okay, so the horizontal asymptote, as we saw here, is the line y equals L, right? Up here, our L value, right? L equals 1, 1. And we said the asymptote was at y equals 1, or y equals L, just like we've said here. The horizontal asymptote will be the line y equals L. So let's just give you a few examples here. Let's just draw ourselves some asymptotes. You can draw them anywhere. I'll draw them here, and here, and back here. Doesn't matter, just draw them anywhere. And I'm just giving you some ideas of what this could look like. So one possibility is that a function goes like this, and it's getting closer and closer and closer. So you can see that the limit as the function approaches infinity is some constant value here. I don't know, say this was 2 right here, then it's approaching 2. But at negative infinity, it does not approach 2 at all, does it? It approaches something completely different. What do you think that's approaching? Infinity, and we'll talk about that on the other side of the page. Another possibility is this, which is very different for horizontal asymptotes than with vertical. So with a vertical asymptote, the function can never cross it. But with a horizontal asymptote, it actually can cross it. See what's happening here? The function's a little ways away from the asymptote, and it's getting closer and closer and closer and closer and closer and closer and closer to the asymptote. And as we keep going out like this, you would say that as we approach infinity here, the function is approaching this y value right there, whatever that dotted line, wherever that dotted line is, the asymptote, that's what it's approaching. So this is another possibility. And another possibility, actually, let's draw another asymptote here. You can have 2 asymptotes, and it could look something like this, for example. Getting closer and closer there, and then closer and closer here. So the limit of this function as we approach infinity is whatever this value is. Let's say it's 2. So if this was the case, say this function is f here, then the limit of f of x as x approaches infinity would be 2. But if this is 5 up here, then the limit of f of x as x approaches negative infinity would be 5. So they certainly don't have to be the same when you're doing these limits like this. Okay, those are just some examples. I was trying to whip through those, and I took longer than I always take too long. Okay, this next bit is very important. You're going to use this idea over and over and over again. If r is a positive rational number, so remember, rational number is any number that can be expressed as a fraction, and positive, you know what that means. If r is a positive rational number, then the limit of 1 over x to the r as x approaches infinity, it's equal to, so let's think about this for a second. So we could have any positive rational number. So this could be, 1, x to the first power, x squared, or x cubed. It could even be a fraction, x to the 2/3, but don't think about that for a while. It might just confuse you. Think of this as being like x to the first, or x to the second, or x to the third. What's the limit as x approaches infinity of 1 over x to the r power? Well, if x is approaching infinity, and this is a positive amount here, this is becoming a massive number on the bottom. Giant, right? So what's going to happen when you divide 1 by a massive amount? Well, if you take 1 pizza and divide it into infinite number of pieces, like an incredibly large number of pieces, how big basically is each piece? Each piece is basically nothing. So this is very important, this concept that when you take some constant amount, in this case 1, and you divide it by x to the r, where x is a positive rational number, you're going to end up with 0. Okay, for all intents and purposes, this is exactly the same thing. This says if r is a positive rational number and x to the r is defined for all x, I'll explain that in a second, it's going to be basically the same thing, then the limit of 1 over x to the r as x approaches negative infinity is also equal to 0. So what's this bit here, this other bit, where x and r is defined for all x? Well, this is just taking into account that we couldn't have something like x to the 1/2, because remember that x to the 1/2 means the same as the square root of x. And if we're putting negative infinity here, that means we're getting bigger and bigger and bigger negative numbers in here. Can you take the square root of a negative number? No, you can't. So, there's the reason why this is written here. If that doesn't make a heck of a lot of sense to you, or if you forget about it, it's not important. I mean, the key piece here is that when you're taking the limit of 1 over x to the r, or 2 over x to the r, or 10 over x to the r, or 100 over whatever, as long as some constant amount here, if x is approaching infinity or negative infinity, you're basically cutting that constant into so many pieces. You're dividing it into so big of a number that you're going to be approaching 0 in both cases. Okay, so that's very important. Okay, so we're going to evaluate some limits here that are approaching infinity. So what you certainly cannot do is just start plugging infinity into all the x's, right? You're not allowed to substitute infinity. Infinity is not a number. So what are we going to do? Okay, to evaluate the limit at infinity at a rational function, so these are rational functions because they're fractions, right? Start by dividing the top and the bottom by the highest power of x. So here we have x squared, x to the first, x to the 0, I guess, x squared, x to the first, x to the 0. So what we're going to do is we're going to divide every single one of the terms by the biggest one. What's the biggest one? X squared. So we're going to have the limit as x approaches infinity of 4x squared over x squared minus x over x squared plus 2 over x squared, all divided by 6x squared over x squared plus 5x over x squared plus 1 over x squared. Isn't this lovely? Okay, then we go through and we simplify. So we have the limit as x approaches infinity. 4x squared over x squared, well, those cancel. I'm left with 4 minus x over x squared. We can cancel 1x, so we're left with 1 over x plus, you can't do anything here, so you still have 2 over x squared, over, cancel, 6, plus, cancel an x, you're left with 5 over x, plus 1 over x squared. There's nothing you can do. So what was the point of doing all this? Well, the point is you can now use that idea we just talked about when you have a constant divided by x or x squared or x cubed, whatever, it basically approaches 0. So we can go through and do this. The limit as x approaches infinity of 4 is 4. The limit of 1 over x as x approaches infinity, that's 1 over infinity, well, that equals 0. Plus 2 over infinity squared, remember, it's just like what we talked about on the other page, plus 0. On the bottom, as x approaches infinity, we get 6. As x approaches infinity, we get 5 over infinity. That equals 0. 1 over 0. Hey, this didn't turn out too bad. What I'm left with is 4 over 6, or 2/3. That's my answer. Now, some of you might be saying to yourself, this is familiar to me. We've actually talked about this before in Pre-Calc 12, I think it was. And what we said is, if the degree of the numerator is the same as the degree of the denominator, so that's what the case is here, degree 2 on top, degree 2 on bottom, the way that you can get the horizontal asymptote is you basically just look at the leading coefficients. So I'm going to erase this. I know you hate when I do this because what are you going to do? But I'm going to erase this and I'm going to write it right here. If the degree of the numerator equals the degree of the denominator, just like we have here, degree 2, degree 2, the horizontal asymptote is at y equals leading coefficient of numerator over leading coefficient of denominator. Why is that going to be? Because you're always just going to have this canceling thing here where you're going to get like 1 over x, 2 over x squared, 1 over x squared, 5 over x, and those are all going to become zeros. So if we look at this, our leading coefficients are 4 and 6, which means the asymptote, the horizontal asymptote, is going to be at 4 over 6, which is 2/3. Y equals 2/3. And that's exactly what we found. So as long as the degrees of the numerator and denominator are the same, that is a quick way you can do it. Okay, let's solve another one. So we take a look at our rational function, and we want to evaluate the limit as x approaches negative infinity. We can't just put negative infinity in here. So what do? We take the highest degree, which is 2, and we divide everything by that. So I'm going to have the limit as x approaches negative infinity of x over x squared over x squared over x squared minus x over x squared minus 6 over x squared. So what does that give us? Well, let's simplify first. So with the limit as x approaches negative infinity, we have x over x squared, which is the same as 1 over x, over x squared divided by x squared is 1, minus, factor out or cancel an x here, you get 1 over x. Nothing you can do here. 6 over x squared. Okay, now we can use that same rule again. If we're putting infinity or negative infinity into this denominator, 1 over negative infinity is basically giving you 0. On the bottom we have 1 minus. If you put negative infinity in here, or infinity, 1 divided by that is 0. 6 divided by 0. So what we end up with is 0 over 1, which is just equal to 0. Our horizontal asymptote is going to be at 0. So there's also a little handy rule I can give you for this, and I'm again going to erase. This time what we say is, if the degree of the denominator is greater than the degree of the numerator, right? Degree 1 on top, degree 2 on bottom, hey, the bottom's bigger, then the horizontal asymptote will always be at y equals 0. So it will always be the x-axis, in other words. That's the equation of the x-axis. Okay, so that's if the denominator's degree is more than the numerator's degree. Now, there's actually a third case which I haven't written down for you. I haven't given you an example of, sorry, but maybe I'll write it down. So here's one case, a second case, here's the third case. What is the third case? This is if the degree of the numerator and degree of denominator are the same. This is the degree of denominator is bigger than the degree of the numerator. So the third case must be if the degree of the denominator is less than the degree of the numerator, then there is no horizontal asymptote. So, yikes, what a mess, horizontal asymptote. So those are the three possibilities when you have these rational functions and you're looking for horizontal asymptotes. You can certainly do this. We divide everything by the highest power of x. It's nice if you understand that. I don't know, maybe some professor at university is going to insist on it, but these are kind of the shortcut ways you can figure out where the horizontal asymptote is going to be. Okay, finally, infinite limits at infinity. I might have to do some more erasing here. Yeah, I do. Infinite limits at infinity are when we have functions that do not approach horizontal asymptotes at infinity. So an example of that would be this one right here. As we go towards negative infinity, this does not approach a horizontal asymptote. It approaches, it just goes up and up and up and up without bound. In other words, it's approaching infinity. So that's an example of infinite limits at infinity. So here's some very simple examples. Y equals x squared. You know what that looks like. I'm not going to spend any time on that. You know it's a parabola with its vertex at 0, 0. So we look like this. So let's take a look at our two limits at infinity. What's the limit of that function, x squared, as x approaches infinity? Well, as we go way out towards infinity, as our x values get bigger and bigger and bigger and bigger and bigger, what happens to our y values? They get bigger and bigger and bigger and bigger and bigger, so infinity. What's the limit of this function, x squared, as x approaches negative infinity? So again, as our x values are getting smaller and smaller and smaller, like really, really small towards negative infinity, what's happening to the y values? They're getting bigger and bigger and bigger and bigger. This is actually infinity as well. Okay, y equals x cubed. Remember what that looks like? Well, let's just throw a few points in there if you forget. 0 cubed is 0, 1 cubed is 1, 2 cubed is 8, 3 cubed is 27. It's up really high there. How about the other way? Negative 1 cubed is negative 1, negative 2 cubed is negative 8, negative 3 is negative 27. It looks something like this. So let's look at our limits there. What's the limit of x cubed as x approaches infinity. Okay, as we go really, really, really big x's, what happens to the y's? Really, really big. They're increasing without bound. But as we look at the limit of this as x approaches negative infinity, what's happening? As we get really, really, really small x values, smaller and smaller and smaller and smaller, what's happening to the y values? They're decreasing without bound. So we're approaching negative infinity. Okay, let's find a couple last limits here. So again, you can never just substitute in infinity here. So please, I'm going to put here wrong. Infinity is not a number. You cannot go, well, infinity to the fourth power minus infinity. And I don't know what you would think that is. A lot of people think, well, infinity to the fourth is still infinity. Minus infinity is 0. No, that's wrong. You cannot do that. So it does not equal 0, I'll say. So what you have to do here is you have to factor. So I'll do it in red for happy correct answer. We're going to factor out an x, and what you're left with is x cubed minus 1. And this is as x approaches infinity. So if we then think of this, what we have is x, well, as x approaches infinity, x is going to be extremely large. Right? We're approaching infinity, extremely large. And then what we have here for the second piece is x cubed minus 1. So we're going to cube an extremely large number. Well, cubing an extremely large number is going to make an extremely large number. And then we're going to subtract a measly 1. I would suggest to you you're still going to have an extremely large number. So what's going to happen when you multiply an extremely large number by another extremely large number? You're going to end up with a massive, extremely large number. We're going to designate that with infinity. You can get as big as you want just by putting bigger and bigger numbers in there. Okay, very similar for this last one. Do not just plug in infinity here. You're going to have to do some factoring. So we're going to have the limit as x approaches infinity. Take out an x. You have 1 minus x then. Okay, so let's think of the two pieces. It's kind of like your fuzzy math, right? If you put infinity in here, well, that's just like what we did here. You're going to have an extremely large number. Okay, when you put 1 minus x, if you put an extremely large number in here, huge number, and then you go 1 minus that number, what kind of number are you going to get? You're going to get an extremely small number, is one way you can think of it, or if you want, you're going to get a very large negative number, right? Think if this is a couple trillion. Well, 1 take away 10 trillion is negative 99999, whatever. Okay, so now we're going to get our final answer. We have an extremely large positive number, and we're going to multiply it by an extremely small number, or an extremely large negative number. It's probably easy if you think of it that way. Extremely large positive times extremely large negative gives an extremely large positive times negative is negative number. So it's going to be approaching negative infinity. Okay, we'll be back to chapter 5 in a couple months. Nice little taste of it for now. Next day, back to chapter 1. See ya.